It's great. Yeah. Started. Yeah, go. All right. I think we just need to share the presentation whenever he's ready. Okay, to do so. Do you want to share your presentation?
Oh, yeah.
Hey. So yeah, thanks. You're cool. So you're good. And then chat. Go on. It's over. How long? It's a great. No. It's just the actual area. Yeah. And I have some sense that he's going to go.
Oh, good.
So he just.
He chose you.
Yeah. I do.
No, I mean, it's okay.
Yeah. I usually have like a few more.
You know, it's okay. Because the thing is, my phone has a heated color.
Okay.
I don't want you anything to dry.
I don't know if it's
Yeah,
Yeah,
that's good.
Yeah.
Ordered it for you.
Thank you so much.
Yeah, even after the, you know, kind of dry coffees. Yeah, just coffee. So,
Yeah. This is what he is. Readings. One reading after.
I see it. You were on there and he was. And it was like a rush day, like. My world. And when I saw it all over.
sure.
Man, I'm happy to help with that kind of stuff. I guess.
Oh,
Because.
Yeah, I mean, so many little things that are repetition. Yeah, and I hope you. So thanks for. Yeah, all one. Yeah.
But to someone's.
And then.
Yeah. No, this is just this.
Yeah, just go. I see.
Oh no, there's a laser here,
Oh, you want?
but it's not working.
No, but you want. Let's see.
Oh, they can't see.
Yeah.
Then
So
I'll
if
just
you-
point.
Or you can just use the.
Cursor. Oh, sorry. Laser pointer.
In case.
So I'm in the same boat, I have to
Is
run
that
out the
context, right?
Yes, well, in beach at 12:30. Okay.
You take over my.
Okay, yeah.
It's like that's
Oh, yeah, she really.
Yeah, before brief.
Sure, okay.
Hopefully I'm still very. I flew in late last night. So, yeah, I will refuel myself.
Yeah, but what? So you keep the weather.
Yes.
Not lying.
People say, maybe once I explained it with somebody else, Chicago Airport. It was so bad.
It's the same.
Yeah, the thing was, I had a deadline, so I immediately finished security and turned on my laptop. It was fine. So I went back to PSC.
Yeah. You can say it. Oh, you like this. Yeah.
Yeah. So negotiate the different models, so it's not like fill up with full authority. It's under the top table code.
So it's 2 minutes to noon, so let's get started. Good afternoon, everyone, and welcome to this EC faculty seminar. And today we have a distinct pleasure to have our speaker, Dr. Gautam Ezila also. He received his Bachelor's of Engineering from Anna University in India, Master's and PhD from UCLA, and then he's currently R&D engineer and an advanced packaging and a deputy director of UCLA CHIPS Center, which is focusing on the heterogeneous integration. And today is going to talk about fan-out wafer level packaging for future HPC systems. Let's welcome today's speaker. Over to you.
Hi everyone, thank you everyone for the warm welcome, and I'm really having a good time in UT Austin. So the title of my talk today is Fan-out wafer level packaging for building future HPC systems. Basically I'm from the Center for Heterogeneous Integration Performance Scaling at UCLA. And I did my PhD actually in the same group. So here's an outline of my presentation. I'll first go over some of the challenges of current packaging landscape for building HPC systems, then talk about how to push the system performance limits using advanced packaging. I'll go over something called as the FlexStrate process, which is actually a patented fan-out wafer level packaging process that was developed at UCLA, particularly for flexible electronics. And then I'll talk about how this FlexStrate or other fault-free processes can be used to build future HPC systems. And then I'll conclude my talk. So before I go into how exactly advanced packaging can be used to build future HPC systems, I want to particularly focus on three important challenges that the current packaging landscape faces. The first important challenge is that transistor scaling is exponential, while package scaling is linear. So what I mean by that is here, this is a typical plot showing, for example, Moore's law, and you can see how with time, you see that the number of transistors in a microprocessor is growing exponentially. On the other hand, if you see how package is scaling, so you see here, this is a comparison between transistor scaling versus package scaling. While transistors are scaling, for example, feature sizes like gate lengths are scaling down exponentially, you see that package scaling, which is shown in the red, is scaling linearly. And you see, for example, here, a typical package dimension, like a bump dimension on a PCB, is basically scaling basically linearly, and it's much slower as compared to the way that transistors on the chip are scaling. So there's an inherent mismatch between the two. So the second important challenge is that die sizes are basically increasing with the year of introduction. So if you look, for example, in the 1990s, like 1995, typical chip sizes were between 100 to 200 square millimeters in area, and they would have about 1 million transistors. But today, if you look at modern GPU chips, for example, from NVIDIA in 2020, in the 2020s, you see that they can go anywhere from 800 to 1,000 square millimeter, and they can have upwards of tens to hundreds of billions of transistors. And the real reason why these die sizes are increasing is because there's an increased functionality requirement of modern chips. They also have a very large embedded memory requirement. And also, if you look at these dies, they have multiple functional blocks in order to increase the parallelism of the system. And you kind of want to put everything together, the embedded memory and all these functional blocks together on the same chip because of the high cost of communication in going off chip. So for example, going from chip to some other component like a memory off the chip. And if you look at most of these, basically this kind of computing systems, they typically have a hierarchical architecture. And because they have a hierarchical architecture, you actually find that they have kind of like a fractal structure, and and mathematically you can show that there's inherently a power law relationship between the area or the size of the chip and the number of IOs that come out of the chip. So because of this reason, which is called as Renz's rule, so the chip sizes are increasing in area with time, and also the number of IOs from the chip are also increasing with time. The third important challenge is that modern computational systems are becoming more and more data-centric, and therefore they demand unprecedented bandwidth. So here you see a plot of the number of AI model parameters in the billions versus year of introduction. So you see that this is also exponentially scaling. And you see how, for example, GPT-3, which was introduced in 2021, has about 175 billion parameters. But when you go to, for example, GPT-4 in 2023, you are looking at around 1.72 trillion parameters. And if you look at all these AI models, fundamentally, they are some kind of a network structure. They have some kind of a neural network, and mathematically they involve some kind of matrix multiplication operation. So when these AI model parameters are basically growing exponentially, what's happening is these matrices are growing exponentially. So there's a great demand in memory in order to store these different matrix elements, and also to store the results of several intermediate steps during this kind of matrix processing. And most of these systems are usually, most of these kind of computing algorithms are also made to run on von Neumann systems where the compute and memory are separate. So this ends up requiring a very high compute to memory data transfer. Here you see how you can see a plot of how these systems actually behave when you improve compute versus when you improve bandwidth. So here you see the overall system performance improvement factor, the increase factor of compute versus bandwidth. So imagine now, say in this case, this was actually a kind of a simulation that was done for ResNet 50 training using 16 interconnected AI accelerator chips. And you can see how if you improve the compute performance, say by a factor of 2x or 3x, there's only a slight improvement in overall system performance. But if you increase bandwidth by say 2 or 3x, you get a much more improvement in system performance. So what this is telling you is that modern AI and ML systems are more bandwidth limited than they are compute limited. So it no longer makes sense for you to just keep pushing computation. You have to now come and try to figure out how you can improve the bandwidth density as well as communication between the chips. So to summarize what these three challenges actually imply for the current packaging landscape, on one hand, you have exponential growth in the number of transistors per square millimeter, and also an increase in the chip size due to the increased functionality demand and complexity of modern chips. And both of these leads to an exponential increase in the number of IOs as well as the communication bandwidth required. On the other hand, you have a linear scaling of package dimensions because of physical limitations in how packages are usually made, which leads to a limited number of coarse pitch IOs which are present on the package itself. And because of this mismatch, what ends up happening is when you actually build systems on a package, you have to use these so-called space transformers or multiple package levels to go from the die level to the PCB. Because obviously, because the die has a large number of interconnects, a large number of terminals coming out, but the number of wires on the PCB are less, and therefore this mismatch needs you to kind of fan it out and serialize the data and then send it to these limited number of links. So there's also the need for components like SerDes. So all these leads to an increase in communication latency, energy per bit, as well as leads to a bandwidth problem. So in a conventional packaging approach, when you're building these large-scale HPC systems, like for example in a server system, you basically require a large number of interconnected compute and memory chips. And current packaging technology with typical the typical kind of ways of packaging them and putting them on a PCB makes the systems very high energy inefficient, bulky, and their performance limited due to bandwidth as well as these latency limitations. So how do you overcome this, right? So in order to overcome this, in a single statement, you can say, due to packaging what you did to the transistors. So the reason why transistors have scaled so much is because you use advanced technologies like microfabrication and lithography to kind of scale down the transistor sizes, right? So you need a new approach to packaging, which from now on I'll call advanced packaging approach, where it basically has three important elements. The first one is that it's a new approach to packaging that uses microfabrication rather than the traditional ways of doing packaging. The second one is that the package dimensional scale down has to match the last metal layer of the chip. So you want the wires on the package itself to have a pitch that's comparable to the kind of terminals that are coming out of the chip. So you don't have to use a space transformer. And third thing, you want to scale out the system, which means you want to be able to build large-scale systems with densely interconnected compute and memory chips. But very importantly, they need to be built on a substrate in such a way that their behavior, their overall electrical behavior, is as if they were monolithically integrated on a single chip. So now you're talking about a situation where you're kind of taking like these kind of SoCs and you're kind of breaking them into a bunch of chips or chiplets, and you're assembling them on this new kind of a package where even though they are physically separate from each other, overall they behave as if they are monolithically integrated. And the way you can do that is by making sure that the interconnects between these dies on the package are very fine interconnects, and also there's a large number of parallel interconnects. So this, for example, is a wafer scale system I'll talk about that we demonstrated at UCLA. So now I'll talk about how to push the current performance limits using advanced packaging. So if you look at current state-of-the-art packaging, how is it done today? For example, by NVIDIA and so on. It's a combination of two things, something called as an interposer technology and 3D. Interposer is also called 2.5D. And what 3D and interposer actually mean is, for example, here you see the memory chip is usually 3D stacked. So it's a bunch of small, thin memory dies that are stacked one on top of each other and interconnected through the use of PSUs. And then the compute chip itself is taken here, and both of them are flip chip attached to this so-called interposer. And the interposer is usually made of silicon or glass, and it has a high density interconnect that connects these two, the compute and memory together. However, let's say this compute and memory together is one module. When you want to basically scale this out and build a large scale system, you have to interconnect multiple modules together. And because of limitations in increasing the size of the interposer, because of, for example, cost and other reasons, you have to actually end up having to assemble this on a PCB. And therefore, you have to kind of match the interconnect density on the interposer with that on the PCB. So you end up having to use multiple layers of packaging that keep increasing or fanning out the pitches all the way to the PCB. So you have, for example, here, you initially started at fine pitch, then you go to C4, the pitches go to around 50 micron to 100 micron, and then once it goes to BGS, it's like hundreds of micron. And so if you look at the top view here, you can see how, from the dense interconnects on the interposer, it goes to coarse interconnects on the PCB, and therefore you now have to get the same bandwidth, you have to send a higher frequency of data through the limited links. So you have to end up using serialization as well as methods such as equalization and so on. So that's what I mentioned here. So you need a space transformer, the interconnect pitches are coarse, and also if you look at these components, they are all packaged and assembled on PCB. So the distance, for example, say you are going from this compute die to this compute die, you have to go through multiple levels of packaging and then PCB and then go reverse. So the link itself is now very long. And so the links start behaving as transmission lines. And signal integrity now becomes very challenging. And you have very complex link designs, such as the use of SerDes, that adds a significant area of overhead to the chip itself. So for example, SerDes can add around 30 to 35% of an area overhead. And similarly, they also add a power overhead. For example, in most of these systems, the data transfer power in going from, for example, compute to memory can be around 30 to 35% of the entire power consumption of the system. So now let's talk about how advanced packaging approach can be used to overcome what we do with conventional ways of doing it. So in advanced packaging, there are two ways of doing this. In the first way, which I'll call as a die last assembly, also called as the interconnect fabric on core substrate. And the second approach is the fan-out wafer level packaging, which I'll call as die first assembly. So in the first approach, what you do is you start with the core substrate, which could be made of silicon, glass, ceramic. And then what you do is you use microprocessing, so back end of line processing, to build high density interconnects on top of this substrate, on this core substrate. And then you can take basically the bare die components, so you can take the bare die compute and memory chips, and then you can flip chip attach them on top of this substrate. And in order to do this, in order to make sure that you can do this at fine pitch, it is necessary that this kind of attachment has to be done directly by using copper to copper, some kind of metal to metal bonding without the use of solder. So either you can use thermocompression bonding, or there's another technique also called hybrid bonding. In the second approach, what you can do is you can basically, this is called as a reconstitution approach, where you take these bare dies, you embed them in some kind of a molding compound, which is usually has to be a low Young's modulus polymer. And then what you do is you then build up the wiring on top of that. And this kind of building up of wiring is called as a redistribution layer. So in this case, the wires are kind of lithographically defined, and they are built again using some kind of backend of line process. So you can clearly see in this case, because you don't use packaging, you don't use packaged components and use bare die components, and there's a high interconnect density on the substrate itself, you don't need any space transformers. You directly use bare dies. And because you use bare dies, you can place these chips very close to each other. In fact, you can get less than 20 micron interdielectric spacing. And also the wires are lithographically defined, so they can be very fine pitch, less than 2 microns. Bump and contact pitches has been demonstrated less than 10 microns. And because these interconnects are now very short and there are a large number of parallel links, as you can see here, you can treat these links now with a simple RC model, like how you would do on chip. And therefore, the design of the driver itself becomes much simplified. And you can drive these links with, for example, a simple cascaded inverter chain. So this kind of a concept it's not just a concept, it's something we have experimentally demonstrated, for example, at UCLA. So here you see, this is based on approach 1. So here, this is actually a 100 millimeter wafer, silicon wafer, on top of which we basically did a dual Lamaxine process and created two levels of metal wiring on top using back-end of processing. And there's also copper bumps. And these are actually, there are there are actually 4 compute and 4 memory dies that are basically flip chip bonded on top of this interconnect fabric using copper to copper thermal compression bonding. And because we use bare dies, you see how the interdielectric spacing can be less than 100 microns. And also because you have, like I mentioned before, you have a large number of parallel links and very short links, you can treat the link itself as with an RC model, and therefore your driver design becomes just simple cascaded inverters. And you can see here how this kind of approach significantly improves the metric, basically the performance metric or the figure of merit of the link itself. So here you see a comparison between various kinds of communication protocols and communication technologies on the board versus Superchips protocol, which is what we call our kind of high density protocol. And you see that we can see that you get a significant, an order of magnitude improvement in the performance of the links. And also you get like a 100x reduction in the area overhead of the driver itself, because you're now going from a SerDes to a simple CMOS-based cascaded inverter chip. So now let me compare these two approaches, so approach 1 and approach 2. So the approach 1, however, does have some issues, especially when you want to push the pitches even finer. And that is where I think approach 2 can be used to build future HPC systems, which will be the main focus of the remainder of the talk. So why that is the case? In the approach 1, if you look at the achievable bump pitch, it involves a mechanical process at the end because you have to kind of pick up the die and then align it and bond it to the substrate. So it involves a mechanical process. So getting less than 5 micron bump pitch is quite difficult. However, in the case of the Colby process, the dies are already embedded in this molding compound and the interconnects are created lithographically. So you're only limited by lithography. So you can even go sub-micron. In terms of scalability, if, for example, you use a silicon substrate, you can only go up to 300 millimeters, but Colby process have been demonstrated even at panel scale. And in terms of fabrication complexity, like I mentioned, die loss needs very complex die-to-wafer bonding, which requires a lot of process optimization. While in the die-first assembly, the Colby process, you can just use standard back-end of line processing. However, there are some major challenges, which is that in the approach 1, the silicon substrate is very thermally conductive. So heat extraction in the first case is quite easy. And also power delivery also is quite easy. And also, if you see, the substrate is the same material as the dies themselves. So they're CTE matched. So mechanically, this is more reliable, for example, in thermal cycling. However, in the fan-out approach, the polymer is organic. It has a very different CTE as compared to the silicon chips themselves. So there will be CTE mismatches and CTE mismatch stresses. And also, it's not thermally conductive, so heat extraction is quite challenging. So from now on, let's focus on approach 2. So before that, I'll take a little step back and talk about the flex rate process, which is going to be a model for the kind of process that's going to be used to build these HPC systems. So what is flex rate process? So flex rate is a fan-out wafer level packaging process that was developed at UCLA to build flexible biocompatible electronics. And what differentiates flex rate from other faulty processes is that it uses a viscoelastic substrate. And uses back-end of line processing, and it has been shown to have it has been demonstrated experimentally with a fine pitch wiring of less than 20 microns for the RDL. And it was particularly designed for making high performance wearables, particularly for medical applications that simultaneously achieves high density integration, mechanical flexibility, as well as biocompatibility. And it was also the main focus of my PhD work. So a little quickly, I'll talk about the comparison between how the flex trade approach to flexible packaging differs from the conventional approach. So in conventional approach, you usually use a thinned organic substrate and you have some metallization on top, and then you flip chip attach the packaged components with some kind of solder. But in the flex trade approach, you just embed the dies in the PDMS and then you fabricate the wiring on top of that. And there are many advantages of the flex trade versus the conventional approach. So in conventional approach, you have coarse interconnect pitches greater than 50 microns, but in flex trade, you lithographically define them so that you can go to very fine interconnect pitches. And here you see solder is required, underfill is required, but no solder or underfill is required in the case of the flex trade process. So mechanically, it's more reliable. And also here, packaged components are used, so the system is quite bulky. But in the flex trade approach, no package is used, just bare dies are used, so you can get very good form factors of the package itself. So how do you actually do the flex trade process? So it's actually it's very similar to a conventional faulty. So first you start with, for example, if you see here, you start with a silicon wafer, which I'll call handler 1. You laminate some thermally debondable adhesive, then you flip chip attach the dies with some kind of alignment, and then you pour the molding compound PDMS. You then compression mold it with a second handler, and the second handler also has a thermally releasable adhesive, but with a higher release temperature than the first one. And then you heat this to the release temperature of the first handler, so the first handler goes out, and then you get this very flat surface with the dies embedded in this molding compound. And then you basically do standard back end of line processing to define your multiple layers of wiring on top. And here you see this is a micrograph of the interconnects themselves. So one of the things we innovated was these interconnects are basically mechanically designed so that they don't crack on the PDMS, because the PDMS has a very different mechanical behavior compared to the much stiffer copper. So a lot of work went into trying to develop basically kind of stress barrier layers between the PDMS and copper. And also, if you notice here, these wires are corrugated vertically. So they go like a vertical serpentine, and that also helps to improve the mechanical reliability of the interconnects. So here you see a large scale system, which is on a full 100 millimeter wafer, which consists around, I think it was around 30 cross 30 array of around 900 dies, 1 millimeter square dies that are interconnected at less than 20 micron interconnected. And one of the key innovations here is the use of PDMS, because PDMS actually has a glass transition temperature less than minus 120 C, which basically means that PDMS can be cured at room temperature. And it also has a Young's modulus less than 2 megapascals, which means during the curing process, it doesn't actually exert much stresses on the dies. And so the dies don't shift much during the curing process and also during operation. And so this improves both the mechanical reliability of the package itself and also allows us to make fine pitch wiring on this substrate. So what can you build with this? So let me briefly talk about some of the demonstrations we've shown. So this was actually a medical device that we both fabricated as well as tested in vivo. So this device basically consists of, it's a multi-channel device, so there are multiple electrodes that are connected at fine pitch to basically a signal processing chip as well as a Bluetooth chip. And so what this basically does is it just picks up electrical signals from your muscle, it digitizes it, and then sends it through a Bluetooth chip to your smartphone so that you can then do post-processing, and you can basically try to study things like arrhythmias and so on. And here you see how flexible this package is. I actually have a sample, so if you guys have time, I can show you. But you see the package is highly flexible. It's also conformable. And you can bend it even to like 5 millimeter or 10 millimeter bending radius without damaging the wires or the die. And here's an example of operation. So the package is attached to, for example, a bicep. And you see with flexing how the basically the device is picking up the muscular signal. Here's another example of a heterogeneous integration demonstrated using the flex trade process. So here we demonstrated a wireless power transfer system on flex trade. And here, if you notice, this is basically a resonant coupling based system. So you have basically an LC, basically a series LC and a parallel LC on the primary and secondary side. And you resonantly couple power, AC power. And then the AC power is rectified with this diode, and then basically a bare die LDO, and then used to power an LED. So all these different components, so you see they are different material, they're made from different material systems. The LED is gallium nitride, then there's the active CMOS LDO, you have capacitors, which are made using deep trench process, as well as diode. And all these different components can be basically be bought off the shelf and then integrated in this platform to demonstrate like a heterogeneously integrated system. So this is to show the viability of using this kind of technology as a general packaging technology to build any kind of flexible electronic system. And here you see some examples of operation where this package is basically attached to basically cylindrical surfaces to show the bending capability and operation. We have demonstrated that the system works well even for bending up to less than 5 millimeter bending radius. So now that I talked about what are the challenges that current packaging faces, how we can basically mitigate this with going to advanced packaging, and talk a little bit about a fan-out wafer level packaging process for flexible electronics called FlexTray. Let me now talk about how we can use fan-out wafer level packaging to build future HPC for AI and ML. So what I'm going to propose is to use basically the FlexTray process or the die-last process for building these HPC systems. And in order to make this happen, two things must happen to the process. One is the scale down of the process as well as scale up. So what I mean by scale down is the current wiring pitches on this on using this kind of RP process is around 20 microns, and the contact pitch is around 20 microns. But you want to reach a target of less than 2 microns if you want to build future HPC systems. And this is according to the NAPMP vision paper. And in order to do this, there are some key challenges that occur when you try to build this in large-scale substrates and when you try to push the wiring pitch down to less than 2 microns. And these challenges can be mitigated with a new kind of way of doing lithography called adaptive lithography with the use of direct write tools. The second is the scale-out strategy. So currently, FlexTray is done on 100 millimeter substrates. But in order to make this process manufacturable, you need to extend it to 300 millimeter wafers or panel scale. And also at the same time, you also need some way to communicate in and out of this kind of wafer scale system. And so you need the development of new kinds of connectors as well as photonics co-integration. You also need novel thermal management as well as power delivery because, as I mentioned, the polymer itself is not thermally conductive. So you need new ways of extracting the heat as well as delivering the power. So to address these challenges, I will talk about some key future technological directions that I can take in research for example, in UT Austin. The first important technology development is scaling the process out to 300 millimeter wafers in panel scale. So currently the process is done semi-automatically at UCLA on 100 millimeter wafers. So this is like, for example, how we do this. So we take the substrate, we laminate the tape using some kind of a manual laminator, and all the pouring of the PDMS, compression molding is all done manually. But eventually you want to shift this to automated tools that can do, for example, the tape lamination, the compression molding of the molding compound and so on. And these tools already exist, and luckily they are going to be installed at the TAI Institute. So one is the scaling out of the process. And so a lot of these key important process steps have to be automated. And also, as I'll talk in the next slide, a lot of new challenges come when you try to push down the wiring pitch to less than 2 microns, and you're trying to build large substrates using this process. So we also need a new kind of way of doing lithography called, which I'll call as adaptive lithography. So why do we need a new approach to lithography? So if you look at the current interconnect pitch on FlexTray, it is 20 microns, and the reason we can't push it further is because it's very difficult to do lithography to define the interconnects. And the reason this happens is because there are two important issues that happen. One is the die shift, and the other one is the surface warpage. So die shift occurs because when you're placing the dies originally on the tape, as I showed before, sometimes there could be some misalignment during the assembly process itself. And sometimes during the curing process of the PDMS itself, there could, because of the shrinkage of the PDMS, there could be some kind of XY shift of the dies or rotation or tilt of the dies. Similarly, there's also surface warpage because most of these polymers, before curing, say you can model them as a bunch of springs. But then after curing, because curing process involves a shrinkage, you can imagine all these springs now want to come close together, and therefore it results in creating kind of like a meniscus on the surface, and therefore you have a bow. And both of these basically lead to a situation where you have both an XY shift as well as a Z shift in the dies. So when at UCLA right now, when we do 100mm wafers, because the polymer that we use has a low Young's modulus, these effects are not that significant, so we can still go ahead with the 20 micron pitch. But if you want to scale this to large scale wafers like 300mm wafers or panel scale, or push down the interconnect pitch to sub 2 microns, we need to basically do lithography accounting for these shifts as well as these kind of warpages on the surface. And so the way we do this, and this is a process that's currently in development at UCLA, and something that I want to continue here at UT as well, is called as TrueAdapt. So what TrueAdapt actually is it's a new way to do lithography, wherein, so imagine you originally had this kind of layout of connecting the dies, but then after you put it inside your molding compound and cured it, the dies are shifted in position. But what TrueAdapt can do is it uses basically a microscope to map out the surface of the wafer, and this is done automatically and at very high throughput. And once the surface is mapped, it then regenerates basically a layout, and then this regenerated layout is used in a maskless lithography tool to print the interconnects to connect the dies together. So irrespective of how the surface is modified, you can kind of use this kind of approach, basically a computer vision based approach, to modify your interconnects so that the dies still end up getting connected. So here are some very basic, like very early experimental demonstrations of this kind of approach. So here you see this is a micrograph of a 5x5 array of dies that are embedded in PDMS. And these were cured aggressively at a high temperature so that the dies have a significant shift. So you see these are the histograms of the die shifts as well as the wattage. And then what we do is using the TrueAdapt process, this is the actual regenerated layout for the shifted dies. And then we use the maskless lithography tool to then print these new interconnects that now successfully connect the basically the wires on the die. And using this approach, we can push the interconnect pitch down now to 5 micron line in space from the original 20 microns. But in the future, you want to keep pushing this technology by improving the algorithm of doing this kind of layout regeneration, as well as use newer maskless lithography tools that have a much better resolution in order to push this process to up to 4 metal layers on flex trade and down to sub 1 micron wiring pitches. And a lot of these tools, especially the tool for doing the maskless lithography, is also coming up in UT Austin in the new TIE facility. So, and finally, the third important direction of research is how to scale out the process to build large-scale systems with the integration of photonics as well as novel thermal and power solutions. So in order to kind of build this entire system and also kind of communicate outside the system, you need some kind of connector or some kind of photonics technology to carry the data. You also need an efficient way to extract the heat as well as deliver the power. So now combining all the things I've talked about in the future work, now I'll give like a small brief idea of how we can kind of build a wafer scale system using all the things we learned so far. Of course, this is not exhaustive. There are also other ways to do this, but this gives a good starting point as to how we can kind of build these kind of systems. So say we start with a handler wafer, 300mm with some thermally releasable tape. We first want the compute dies, the memory die, and the silicon PIC. And then we can compression mold this low Young's modulus polymer. It's very important that the polymer that we use has to be low Young's modulus, less than 10 megapascal, so that it can be basically compliant and viscoelastic, and also ensure that it has low die shift and CT mismatch stresses. And then we debond the first handler, and then we can define the RDL on top using the TrueAdapt process I mentioned earlier. And you can also have a little space here for attaching the fiber optic connector. So then you can do a kind of 6-axis optical alignment using active alignment to attach, for example, here I've shown a QPC, a quasi-planar coupler, to attach optical fibers to enable high-speed data communication. And then what you can do is to deliver the power. If you see here, when you're building these large scale systems, a single 300 millimeter wafer, you can estimate that the power consumed can exceed around 30 kilowatts per wafer scale system. So you're looking at a power density of more than 4 watt per square millimeter typically, right? So the only way you can deliver this power is using some kind of 3D way of delivering the power, basically vertically delivering the power. So the new kind of way this can be done is what I call using a mechanically compliant 3D power backplane. So what this is one side is basically a rigid substrate that has power management ICs that are bonded on top using TCB or hybrid bonding. And on the other side, you basically have this compliant layer that kind of matches the Young's modulus of the compliant layer that holds the dies. And then what you can do is you can do a polymer hybrid bonding to attach this. So you now have this 3D, you have this 3D stack on top that can deliver the power vertically. And then the bottom substrate can be removed, and then the PDMS can be removed by some kind of laser drilling process. And then you can deposit a thin heat extractor in the back. And then, so why this compliant layer really matters is because if you look at the Young's modulus of copper, it's around 4 orders of magnitude more than interlayer dielectrics or this molding compound. So for all intents and purposes, you can assume that everything, all the metallization is rigid, including the dies, and everything around it is actually like a bunch of springs. So imagine one of the dies was getting heated, then what happens, this die would expand, but the stress of this expansion is basically distributed among these compliant layers. So it actually would reduce the chip package interaction and also improve the overall mechanical reliability of this package. And so finally, after this kind of assembly, what you can do is you can put a heat sink on top and bottom to extract the heat. And then to scale out the system, say to a data center scale or something like that, you can have a bunch of these systems connected with optical fibers. And then you can use some kind of advanced cooling method to extract the heat both from the die side as well as the power delivery side. So this is like, it's like a vision of how I think FlexStraight can be used for building a HPC system, but how it is not exhaustive. Usually with these kind of experimental projects, you have an idea, you go through it, and then you discover issues that you have, and then you have to kind of change the plan, and it keeps going like that. I particularly focus on HPC, but FlexStraight can be used for also the same technology can also be used to build more complex biomedical systems because you can heterogeneously integrate all kind of components like, you can integrate sensors, you can integrate different types of signal processing chips. We are also looking at how to integrate microfluidics into this kind of a package. So you can really build very complex medical devices as well. Yeah, so this actually, I don't want to get into this, but basically this was my overall kind of research plan, we can say, because in order to make something like this happen, it's very interdisciplinary because you have on one side, you have the architecture side, you need to partition the system and how you, and on the other side, you have the manufacturing, the fabrication. You also have a lot of modeling work that has to go in because the package, you have to consider thermal effects, mechanical effects, electrical effects, and so on. So these are some 5 important research areas that I can identify, and all the challenges that occur there, and also possible collaborations, which I will discuss when we get to it. And in terms of facilities, a lot of facilities that is needed to do this kind of research already exists at UT Austin. A lot of the manufacturing tools for taking this kind of process to industry already is going to come up at TIE. And a lot of existing tools also exist in my previous lab at UCLA as well as in IIT Madras. And I also want to emphasize that this is a very highly interdisciplinary work, and it requires a lot of collaboration between EC, material science, as well as mechanical engineering. And I think that packaging is something that has gained a lot of interest, especially in the past 3-4 years, especially with the NAPMP. And so I think that having a kind of focus on packaging at UT Austin in terms of having courses and research develop the next generation of engineers for packaging is something that is definitely very important for UT as well as Texas. So to quickly conclude, there are several issues that are with conventional packaging, and FlexStraight is a new way of doing fan-out roll packaging using basically a low Young's modulus polymer. And in order to build future HPC systems, the current process must be scaled out and scaled down. And obviously, there are several challenges that this has, several challenges that requires a lot of collaboration. And I feel that UT Austin is a great place to do this kind of research because of state-of-the-art facilities that are already present here and are going to come up at TIE, and also a lot of world-class faculty here that are doing a lot of interdisciplinary research. So thank you. I would like to acknowledge my professor and also the group. And thanks a lot.
Because maybe it's gonna leave. Yeah.
Is there any question from the audience?
Yeah.
I thank you for your presentation. It's an interesting topic. I only have two questions because I have no idea how to do the like packaging design. I'm curious what kind of tool are you using to run the simulation for like the 3D packaging because there are multiple layers. And second question is there any suggestion for the beginner that are interested in this field?
Okay, so to answer the first question, a lot of package simulations that we do are in console actually.
Also,
Yeah.
they are not single tool. There are a lot of them.
Yes, because a lot of multiphysics, like a lot of interactions happen. Like for example, when you are when there's a die that's getting heated, right? There's a thermal effect, but there's also an effect on the behavior of the chip. So there's an electrical effect, and then there's also a mechanical effect because the chip is going to expand, and there's going to be other things around it that is going to expand differently, and it's going to cause stresses and all that, right? So actually doing multiphysics modeling to design packaging is an active area of research. So it is something that right now people they do it, but they kind of do it separate from the design. But in the future, you need to have design taking into account all of this. Your second question, I didn't get.
Is there any suggestion for the people who want to start with this kind of packaging research?
Yeah, so from if you're going to actually, like for example, be a student and doing research in this, right? So I think that the main thing here is that from fabrication perspective, like from like how you're going to make this, right? It's actually quite elementary. If you compare to front end, the processing here is very simple. It's all standard, like it's just depositing dielectric, using contact lithography, etching holes, and then filling it up with copper. That's process-wise, it's very simple, right? But so anyone can actually go and actually try to kind of build these kind of systems. It's not that easy. But building the ecosystem, right, of trying to have like considering all aspects of the problem, from the wafer to power delivery to thermal management, different materials, different ways of simulating, and also building an ecosystem for architecture and stuff like that. I think that is where the research perspective.
Yeah, okay. Thank you.
Yeah.
Thank you for the great talk. So the true adapt method seems to be a nice way to deal with the problem you have, which is the misalignment of the polymer. But I mean, eventually, you need to solve the misalignment issue. Can you talk a little bit about what would be required to get them? Because it's going to limit your density, right? You have to have them far apart so they can misalign. So what is the path to solving?
So the thing is the misalignment. So in this case, the misalignment. Sorry, in this case, the misalignment was actually exaggerated because so the PDMS, the amount of like misalignment the dies have during curing depends a lot on what temperature you cure. So if you cure at high temperatures, it's more misalignment. But in this case, it was cured at high temperature. But usually when you cure PDMS at room temperature, right, over 100 millimeter wafer from one end to the other, you have only around 6 micron misalignment. So the modified mask, like here you see, I don't know if you can clearly see here, but these interconnects are not going straight. They're actually bending slightly here and then bending over there, right? That's enough to connect all the paths. So you want the substrate to be low Young's modulus so that you get minimal shift across a large substrate, and then any extra shift you will accommodate with the true adapt.
Okay, so you're kind of it's doing its job. You don't really need it to.
Correct. Okay. If you say have a die that's like completely like this, right? That's not good. That won't work.
Thank you.
Yeah.
Oh, yeah. On, I think it was maybe like slide 54, 55, where you backfill with copper for thermal management.
Yeah.
You sort of make the argument that if you have local heating of one of these components, the distortion is sort of distributed. Does that make any assumptions about like the interface between the upper heat extractor and that particular component? Like, are those mechanically rigidly coupled to one another?
Yeah, they're rigidly coupled. So if you're actually simulating this, there will be a slight bend in this.
Yeah, okay,
Yeah, but the idea is it's compliant enough that nothing breaks.
gotcha. Excellent.
Also, this is an idea, it's not something, yeah.
Yeah, and I missed the point here, but you said kind of low Young's modulus here.
Yes,
Then which means it's more flexible, right?
correct.
But then that creates all those kind of misalignment shift.
No, they are already connected.
Okay.
So in this case, everything is already connected. So from, even though there's material in between, right? But mechanically, you can consider it as empty space because it doesn't really matter that much. So this whole thing will behave like a compliant mechanism. So it's like every time there's something stressed, the things around it, so these things are going to behave as beams basically, and they're just going to bend. But they won't bend to the extent that they will cause this bond to break. Because also the dielectrics here have corrugated interconnects, so they are also compliant. They are also slightly stretchable. So you have this, all the interconnects are in this compliant substrate, so that basically any kind of CTE mismatches can be accommodated by the.
Yeah, so you mentioned that the thermal dissipation in chip first technology is kind of a problem and hasn't been resolved. So what do you think about this kind of issues can be resolved by materials or some EVA algorithm will help?
Sorry, can you?
So you mentioned that the thermal dissipation in chip first technology has some problems and haven't found a good solutions yet. So what is your?
Oh no, I said chip first, yes. So chip first is the Falpy process, right? Yeah, in Falpy process, thermal management is difficult because there's no way to there's no way to extract the heat because everything surrounding the die is non-thermally conductive.
Yeah, so what do you think about how can resolve these kind of problems by doing some metallizations or new materials?
Yeah, so new materials is something like you can have, like for example, you can embed like a mesh in the polymer itself to extract the heat. So imagine like you have concrete with rebar, right? You can have PDMS, but it can have a mesh of copper embedded in it to extract the heat. But any kind of polymer you're going to use is not going to be thermally conductive. And when you start adding fillers, right? Imagine I was adding a conductive filler to the polymer, right? It starts losing that mechanical property you want. You know what I'm saying? So like I feel, I don't know, maybe there's a better way to do this. Maybe there's a material out there that's both compliant and conductive. But the way I think of this is to just have this kind of an actual metallic heat extractor, which is touching the dies to. Yeah. And also, if you look at, I'm not very sure because a lot of these technologies are also done in industry, so a lot of details are hidden. But if you look at TSMC also has a vapor level packaging process based on Falpy. In their case, also they do some kind of 3D heat extract. Because when you go to these high power densities, doing it 3-dimensionally is the only way you can do it.
If there's yeah, let's check the. Is there a question from the Zoom audience?
Yes, I have a question. Can we go to slide 47?
Yeah.
Thank you. So this is very exciting. I see that the RDL does not completely cover the silicon photonic integrated circuit. And I'm wondering about the, if you have, say, 4 metal layers, you will have a degree of topology there that may impact the manufacturing. Can you discuss the manufacturability and whether or not this has been demonstrated for the side of the RDL as it uncovers the silicon photonic integrated circuit?
Right, as far as has it been demonstrated, I'm not really aware of any literature that talks about doing this. Also, I haven't seen any literature that talks about attaching a connector to a substrate that's very soft, because obviously there's going to be like issues with like planarity and all that, right? So yeah, so this is something definitely like I have to like kind of think about how to actually do this. But as far as I know, there's no literature on how on being demonstrated.
Thank you.
Okay, I have another question. Just give me your time. So for the corrugated copper, do you know how they did that fabrication? Are you involved in that, or talk more about it?
Yeah. So the way we design those interconnects is first we model them in ANSYS. So we model depending on the size. So depending on the width of the interconnect, right? The periodicity of the corrugation changes, the optimal periodicity for getting the mechanical reliability. So you basically first you do mechanical simulations and find out the optimal periodicity as well as the height of the corrugation. And then the corrugation itself is made of some kind of polymer, like it could be done with polyimide or something.
Yeah, I'm just trying to picture the fabrication, how you grow it corrugated.
Oh, it's there actually here. It's here. Yeah. So this is that corrugation. You see those pillar kind of things? Yeah. Yeah.
Pattern like
Yeah,
on
yeah,
top of some, on top of polymer, this pre-pattern.
Yes.
Is that, okay,
Yeah.
that makes sense. Okay, thank you.
Yes, it's about to rain also. Yeah, let's send our speaker on the line.